about the chemistry of S block elements, that is alkali metals and alkaline earth metals. Today, I would like to draw your attention to the chemistry of P block elements. As you all know, main group elements are classified into two categories. One is S block, consists of two groups, and P block consists of 6 groups with regular addition of electrons from P1 to P6. That means group 13, 14, 15, 16, 17 and 18. In the group 13, we have, this is the P block, about 30 elements are there, excluding helium. And in the group 13, we have 5 elements are there. Start with boron and aluminum, gallium, indium and thallium. And in the group 14, we have carbon, silicon, germanium, tin and lead. And in group 15, also called nitrogen series, we have nitrogen to begin with, and then we have phosphorus, arsenic, antimony and bismuth. In the group 15, oxygen series, also called chalcogen series, we have oxygen, sulfur, selenium and tellurium. And in the group 17, we have halogens, fluorine, chlorine, bromine and iodine. And lastly, we have inert gas elements such as neon, argon, krypton, xenon and radon in group 18 along with helium. And these 30 elements dominate P block chemistry. And let us discuss one group at a time. To begin with, let's start discussing the chemistry of P block elements such as group 13. In the group 13, we have boron, which is typically a non-metallic element with little metallic characteristics, and rest of the metals such as aluminum, gallium, indium and thallium, all are metals, and all group 13 elements show little higher ionization energies or ionization enthalpies compared to alkaline earth metals. However, higher ionization energy for removal of free electrons is anticipated in case of boron compared to the rest of the elements because of the smaller size. And similarly, there is some the difference in the chemical properties also one can see between boron and rest of the elements. And aluminum has many similarities with beryllium that I discussed while discussing the chemistry of alkaline earth metal elements. For the group 13 elements, group of state is +3, that is a stable orbital state. Because they have S2P1 electronic configuration, all the 3 electrons can be removed to generate a trivalent cation, and hence the group shows +3 as the most stable orbital state. And stabilization of lower orbital state for the heaviest elements is not possible. That's only thallium in this case. And +3 state compounds of thallium are highly oxidizing. That means it has a tendency to getting reduced to thallium +1 state to retain those S electrons in its place, and this is called inert pair effect. And I would elaborate more about inert pair effect later. However, this inert pair effect is more pronounced among other elements of group 14, 15, 16. In case of group 14, it is tin and lead. In case of group 15, it is bismuth, and in the case of group 16, it is tellurium. These 5 elements have little tendency to unpair the S electrons to promote to P orbitals to show the group of state. And whenever such oxidations are possible, those compounds are highly oxidizing in nature. So boron is a fairly rare element, and abundance is 0.001% by mass in the Earth's crust. That is, it is the 34th most abundant element in the Earth's crust, and it has 2 isotopes. One is 10 boron. This is about 19% abundant, and other one is 11 boron. This is about 81% abundant. spin for 10 boron is I equals 3, and in case of 11 boron, I equals 3 by 2. The most common sources of boron are tourmaline, that is boron oxide or borax, that has a composition Na2B4O5 OH 4 times and 8 equivalents of water. This is called tourmaline. There is also another ore mineral called kernite. The composition is more or less same, but differs in the water hydration. So just if you look into this one, they are nothing but hydrated sodium borate hydroxide minerals. It is not very easy to purify boron, and one method that is used for purification or reduction of boron is using magnesium. One can take boron trioxide, pure boron trioxide, and subject it to reduction using magnesium. It gives pure boron along with magnesium oxide. The oxide is made by melting boric acid. One can heat boric acid and to get rid of hydrogen, and get B2O3, and then high purity boron can also be obtained by converting combination of boron trichloride or boron tribromide, combining with hydrogen and passing through consider boron trichloride or boron tribromide. Along with hydrogen, it has to be passed over a heated tantalum oil. Results are better when the hot wire temperature reaches 1000 degrees centigrade. So boron crystallizes in a variety of forms, all containing icosahedral petrol unit. You can see here, this is one of the borate minerals. This is how it looks. This is how the icosahedron looks like, and I have a model to show you here. And this is icosahedron. It has 12 vertices. You can see here 5 are here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and one axial here, one axial here. So we have 12 vertices are there, and then we have 5, 10, 15 plus 5, 20 triangular faces are there, and 30 edges are there. That means the icosahedron has 12 vertices, 20 triangular faces, and then 30 edges. So this is how crystalline boron looks like, and it has several forms. All of them have this icosahedral structure. And you can see other space filling model is shown here. In this one, it shows arrangement of 12 boron atoms in this icosahedral fashion. So aluminum is third most abundant element in the Earth's crust. That's about 8.3%. We know the most abundant one in the Earth's crust is oxygen. Next one is silicon. Third one is the aluminum. And the common or most common ore of aluminum is bauxite. And there is one more ore of aluminum that's called cryolite.
শনিবার করে দেখতে হবে ভালোভাবে করতেই পারিস না টিভিটার সময় লাগানো না
অ্যালুমিনিয়াম অক্সাইড
সেই সাইডে সরতে পারছিস না
another
আগা একটু হ্যাঁ তো উঠা লিখাটা
hexafluoro sodium aluminate sodium hexafluoro aluminate
ধরে রাখ না
okay and bauxite contains
এদিকে লিখা আছে সেখানে তো নরমাল যাবে
mainly iron oxide such as Fe2O3 silicon dioxide or silica and several other impurities. In order to isolate pure aluminum, these impurities must be removed. This is done by a method called Bayes process.
ধরতেও পারছিস না তুই ধুর তেরিকা ছাড়তো
So in this process, what they do is initially this bauxite is treated with sodium hydroxide to eliminate sodium silicate and form sodium aluminate. It forms sodium aluminate. Of course, silica also reacts with sodium hydroxide to form sodium silicate. The bauxite treatment with sodium hydroxide gives these two, which results in the formation of sodium aluminate and sodium silicate. So iron remains as a solid, and when CO2 is blown through the resulting solution, sodium silicate stays in solution while the aluminum is precipitated out as aluminum hydroxide. The second step is the blowing carbon dioxide through this sodium aluminate reacts with carbon dioxide to form aluminum hydroxide. So the hydroxide can be filtered off, washed and heated to form pure alumina. So this aluminum hydroxide
আমার দিয়ে দিবি আমার দিকে পিছন দিয়ে দাও আমার মুখে যা
on heating.
So this is about some element by chemistry in IIT Delhi.
So in the next stage,
and Saturday
the formation of pure alumina from aluminum oxide